What if the simplest idea in AI, one that was declared dead in 1969, turned out to be the seed of everything? This is Forward Pass AI. We build neural networks from the ground up, one concept, one episode at a time. No shortcuts, no hand-waving. By the end of this series, you will understand every layer, every gradient, every decision that makes modern AI work. The perceptron, from promise to failure to resurrection. Your brain is made of roughly 86 billion neurons. Each one does something deceptively simple. It collects signals from its neighbors, combines them, and decides whether to fire. A perceptron is the mathematical skeleton of that idea. The perceptron takes a set of numerical inputs, call them x1, x2, and so on. Each input represents one piece of information about the world. Each input has a weight, a number that says how much that input matters. A large weight amplifies the signal. A weight near zero ignores it. A negative weight flips it. The perceptron multiplies each input by its weight, then sums everything up, plus a bias term that shifts the threshold. Then comes the decision. The perceptron applies a step function to that sum. If the result is 0 or above, the output is 1. The neuron fires. Below 0, the output is 0. It stays silent. One input, one decision. The perceptron was invented in 1958 by Frank Rosenblatt, a psychologist and computer scientist at Cornell. He wasn't just writing equations. He built a machine. The Navy funded the research, and the press ran wild. The New York Times reported, and I am quoting directly, that Rosenblatt had built the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. What it could actually do was classify linearly separable data, place a straight line between two groups of points. Remarkable for 1958, but not quite consciousness. The Mark I perceptron was a physical device. 400 photocells fed signals into a patchboard of hand-wired connections. Electric motors physically turned potentiometers to adjust the weights during learning. It looked nothing like the neural networks we draw on whiteboards today. In 1969, Minsky and Papert found the crack in the foundation. They asked, can a perceptron learn XOR? XOR, exclusive, OR, takes two binary inputs. It outputs 1 when exactly one input is 1. 0 and 0 gives 0. 1 and 0 gives 1. 0 and 1 gives 1. 1 and 1 gives 0. Plot those 4 points on a two-dimensional grid. The two ones, the positive outputs, sit at the top left and bottom right corners. The two zeros sit at the other two corners. A perceptron classifies by drawing one straight line through the input space. For XOR, no such line exists. Try the main diagonal. It cuts through both classes. Try the other diagonal, same problem. Rotate it any way you like. You cannot separate these 4 points with a single straight line. This is what it means for a problem to be linearly inseparable. Minsky and Papert formalized this in their 1969 book simply titled Perceptrons. They proved mathematically that a single-layer perceptron could never solve XOR. Not with better training, not with more data. It was a fundamental geometric limitation. The book's conclusions spread quickly. Funding for neural network research collapsed. The field entered what historians now call the first AI winter, over a decade in which the whole paradigm was considered a dead end. One book, one proof, a decade of silence. Let's build one from scratch. No libraries, just Python. Every line will be visible, nothing hidden behind an import. We define a perceptron class. The constructor takes the number of inputs and a learning rate. It initializes the weights as zeros, one weight per input, and the bias as 0. The forward pass computes the weighted sum. We multiply each input by its corresponding weight and add them all together, then add the bias. This is the core computation. Everything else in a perceptron flows from this single number. Then comes the step function. If the net input is 0 or above, return 1. If it's below 0, return 0. This is the decision boundary, the moment the neuron commits to an answer. Let's test it on the AND gate first, the easy case a perceptron can solve, and is 1 only when both inputs are 1. We set up the 4 possible input combinations and their expected outputs. Before training, all weights are 0. So the net input is just the bias, also 0. The step function returns 1 for any input. Our perceptron predicts 1 for everything. It hasn't learned anything yet. That's the forward pass. Now we need to teach it. The perceptron learning rule is elegantly simple. After each prediction, we compute the error, the difference between what we wanted and what we got. If we're wrong, we nudge each weight in the direction that would have helped. In code, we loop over the training data for a number of epochs. On each example, we predict, compute the error, and update every weight and the bias. We repeat this until the weights converge. Let's trace one update manually. Input is 1, 1, target is 1, prediction is 0. We're wrong. Error is 1 minus 0 equals 1. Each weight gets nudged up by the learning rate times 1 times that input. The bias gets nudged up by the learning rate. Slowly, the boundary shifts. After just a few epochs on AND, the weights settle. The perceptron stops making mistakes. We call this convergence, and it's guaranteed for linearly separable problems. The perceptron convergence theorem promises it will always find a solution, if one exists. After training, the weights have shifted from 0 to small positive values, and the bias has become negative. These numbers encode the AND function. The perceptron has learned. Back to XOR. A single perceptron cannot solve it. The problem is not linearly separable. But what if we didn't use a single perceptron? Stack multiple perceptrons in layers. The first layer, the hidden layer, transforms the raw inputs into a new representation. The second layer, the output layer, classifies that new representation. With the right hidden layer, XOR becomes separable. But we also need to swap out the step function. Training a multi-layer network requires gradients, rates of change, and the step function has no gradient. It's a cliff, perfectly flat on both sides, vertical jump in the middle. The sigmoid function gives us a smooth S-curve instead, always differentiable, always usable for gradient descent. A tangent line can touch it at any point. The gradient always exists. Here's the intuition. The hidden layer acts like a coordinate transformation. It bends and folds the input space into a new shape where the XOR points can be separated by a line. What was geometrically impossible in the original space becomes possible in the transformed space. In code, a minimal MLP for XOR needs just 2 hidden units. We define a sigmoid function, a forward pass through 2 layers, and use hand-tuned weights known to solve XOR. This is not training, just demonstrating that a solution exists. XOR solved. From one neuron that could draw a single line to layers of neurons that can represent any function, that is the arc of this story. The perceptron was not a failure. It was the first rung of a very tall ladder. In the next episode, we go inside a network while it's learning. We'll follow the gradient backwards from the output's mistake all the way back to the first layer's weights. That's backpropagation. See you then?